Bismillah ar-Rahman ar-Rahim. Good morning, class. This is our 13th episode. It's gonna be about the stoichiometric reacting masses, calculation of stoichiometry, and I will talk about the limiting factors, about the Avogadro's number, all things that related to mole. There are 8 subjects. The first one of them is for the core. So it is a state the concentration can be measured in G per decimal cubic and mole by decimal cubic. And also, there are other 7 subjects for supplement or extended students, and they are here in this list, and you can easily go through them and know what is going on about them. I'm not going to talk too much about them because I have already done this at the beginning of our 5th chapter, and I will proceed to today's topic. Okay, now we would like to start our today's period or lecture. It is going to be about the mole and the chemical equation. In particular, we are going to study how to calculate reacting amounts. Let us assume that we have calcium carbonate and we are going to heat this calcium carbonate to the end. Calcium carbonate actually is the limestone, limestone. And when we heat it, it's gonna react and actually split into calcium oxide and carbon dioxide. So we would like to know how we can make the mole ratio, how we can express them in gram, how we can determine the MR, which is the relative molecular weight or formula, and how to express them in gram, and also to find out the ratio between the components. Now, if we have our calcium carbonate here, I bring from here, from the table, from the periodic table, I bring each square for each of these compound that makes calcium carbonate, which those elements are sharing to each other. When they react to each other, they give us calcium carbonate. So the calcium carbonate is form of calcium ion, carbon, and 3 oxygen. This is the formula of calcium carbonate. And then when we heat it, this is the delta, and the delta is the symbol of heat. Then it's going to dissociate into calcium oxide, which is the lime or calcium oxide, and carbon dioxide. When we make a balanced equation, it's going to be like this. Calcium oxide, 1 oxygen, with 2 oxygen of carbon dioxide. Those are 3 oxygens. Here we have 3 oxygen atoms. We have only 1 calcium atom and 1 carbon atom. So it's balanced now. In step 2, we are going to see the ratio, the mole ratio. So if we say 1 mole of calcium carbonate, this is 1 mole of calcium carbonate. It will give me 1 mole of calcium oxide in addition or plus to 1 mole of carbon dioxide. So this is the mole ratio. Now I'm going to determine the relative molecular uh, formula of each compound, and also the mass of each compound depends on them. So it's going to be 40. Calcium is 40 plus 12 of the carbon, and then I have 3 atoms of oxygen, each one of 16 is going to be 14 plus 16 plus 12. And here, because this is calcium, I have only 1, and oxygen is 1. And here we have carbon, which is 1, which is 12, and 2 oxygen. So when we add those together, we are going to have 100 mole of um, calcium carbonate. When heated, it's going to give me 56. When we add this together, 56 moles of calcium oxide and 44 moles of uh, carbon dioxide. This is the mole ratio. Okay, and then when we express the mole ratio in grams, we are going to have the mass. So 100 gram of calcium carbonate will dissociate and give me 56 gram of calcium oxide and 4 grams of carbon dioxide. And then step 5, that will determine the ratio, which is 100, this one, or this one, 56 for calcium oxide, and 44 for carbon dioxide. Now, by those 5 steps, we determine the ratio. And it is very important to me to determine the ratio because I'm going to use it in the coming problems to determine a specific amount in a given problem. Let us go and see what is in. Now, let us use the previous example in order to determine the masses of some of the components or all of them. So how we can do that, and how we can use the previous information of the last example to do that. Our example says that calculate the masses of product if 8 grams of limestone, which is calcium carbonate, is completely heated. When we say completely heated, that means it is completely burned. That means it's used all of the calcium carbonate present. So the whole 8 grams of limestone have been heated and completely composted. Now, calcium, the first step, as we said that last time, that we have to write a balanced equation. So this is the balanced equation. Calcium carbonate, 1 mole of calcium carbonate. If heated to the maximum, it's going to give calcium oxide plus calcium plus carbon dioxide. And why it happens like this? Because actually when you heat it, it is going to be dissociate into its component. Now, 1 mole of calcium, that means now we are going to pull out the mole ratio here, and it's going to be 1 mole of calcium carbonate when heated gives 1 mole of calcium oxide and also 1 mole of carbon dioxide. Then we are going to determine the molecular mass of each, or the molecular relative molecular formula of each. Then it's gonna be this way. It is 100, as we said last time, to 56 to 44. It's gonna give me this one. I'm going to express this in grams, so it's gonna be each 100. If I burn completely 100 grams of calcium carbonate, is going to give me or will produce 56 grams of calcium oxide plus 44 grams of carbon dioxide. The ratio that I need is 100, 55 and 44. This is up to step 5. Now, what are the new calculations? He asked me to his demands, which are the masses of the products. So he wouldn't like the reactant, he wants the products. If 8 grams of limestone, so the use of limestone of only 8 grams. So here I have 100 grams here. I don't need 100 grams. I need only 8 grams. So 8 grams, how many of them are going to be here? It is just simple calculations. 8 grams of calcium carbonate equal 100% based on what he gave me here. Then calcium oxide is 56%, which means if I multiply 8 by 56 and then divide them by 100, it's going to be 4.48 grams of calcium oxide. And at the end also I have carbon dioxide, which resemble 44%, which is here. This is 100%. 100% yield into 56% and 44%. And this, when I did this mass, is going to be 8 multiplied by 44 over 100 equal 3.52 grams of carbon dioxide. And this is the way that I solve all problems. And we are going to practice together more 5 problems in different segments so we can understand what is happening. Now, why I bring this again, I bring this from the table in order, because here he didn't give me anything about the relative atomic mass of each one of them. So I pick it out from the periodic table and bring each one here in order for us to see and visualize what is happening. So just follow my steps and you are going to be bro in stoichiometry. Go for the second one. In our previous example, we use only 8 grams, a small amount, that is just only 8 grams of calcium carbonate, the limestone, and we just say that it's going to be burned to the maximum completely, and then we ask about how those masses are going to have. Now we are going to increase such ones. We are going to increase this one in order to know how we can deal with them. What do I mean by that? What do I mean by that is very simple. Is that instead of having 8 grams of limestone, which is calcium carbonate, now we are going now here in this problem, we are going to have 5 kilograms of limestone. We would like to burn 5 kilograms of limestone. So what we are going to do? Nothing. Simple. Very simple. we are going to have the main 5 steps that we are already have. Balanced, starting from the balanced um, step number 1, which is the balanced equation, till the having the mole ratio of each. Step number 5. In step number 6, we are going to do the same things as we did with the previous example. The only difference here, and you have to be sure about that, is that you are going to convert this 5 kilogram into grams. So you are going to have it here that 5 multiplied by 100, and this is your way of doing this, and that's it. When you change it, you do the same as you did in number 6, and you are going to have your problem solved. Very easy. Go step by step and you are going to be pro. Here is our second example. It's going to be a little bit hard and little bit indirect. We would like to now, from now on, we are going deeper so we can understand what is going on. So our example says that what mass of aluminum oxide is produced when 9.2 grams of aluminum metal reacts completely with oxygen gas. When we say reacts completely with oxygen, that means oxygen is abundant. There should be no aluminum after this reaction. So what I'm going to do is I'm going to follow my steps, and I may squeeze something and recall previous information that I have in order to solve this problem. So the first thing that I'm going to do is to write a balanced equation for such reaction. Why? Because it's not given here. Here he just gave me the aluminum oxide produced, aluminum mass, and that's it. So it's going to be like this: 4 aluminum atoms reacts with 6 oxygen atoms to gives me 2 molecules or 2 uh, relative formula or molecular formula of aluminum oxide. Okay, now I'm gonna convert this into mole ratio. So 4 mole of aluminum is gonna react with oxygen. I don't need anything about oxygen because oxygen here is only a reactant, and gives me 2 mole or produce 2 moles of aluminum oxide. That means the ratio is 4 mole to 2 mole, or 2 to 1. Both of them are right. I'm going to use 4 to 2. Now, then I'm going to do what we call it the footbridge steps, or steps of the footbridge. What is the footbridge steps? If a footbridge is the bridge where pedestrians move through. Okay, like if you have, for example, a railway, then there is a pedestrian bridge over it. So the footbridge means a bridge that overlap some places in order for the pedestrians to move through. And the footbridge is like this up, plateau, and down. So it's going to be up stage. The plateau stage is called, had another name, which is cross stage, and then the down stage when you are come out from the bridge. So now in this bridge, the first thing I'm going to have is to know the numbers of moles of each one. So how many, the number of moles of aluminum in 9.2 grams of aluminum. This is the math that I have. So I need to know how many moles in this, how many moles of aluminum in this. In mine, I'm going to use this one also. But here, in order to bring the moles, if you just remember what we have studied before, that the number of moles equal the mass in grams over the molar mass in gram per mole. So the number of moles of aluminum is 9.2 grams over 27. From where I get this 27 gram of mole? This is from here. It is the relative atomic number of aluminum, and it's going to be 0.34 moles. So in each 9.2 grams of aluminum, there is 0.34 mole of aluminum. This is very important in order to do this. So I have it here. The number of moles equal the mass in grams over the molar mass, and then this number of moles of aluminum equal 9.2 over 27 grams per mole equal 0.34 moles. So now I determine the number of moles on the amount that have been given to me or has been given to me in the problem. Let us move and see stage 4, 5, and 6. Now, in step 3, up stage, we determine the numbers of mole, or we count the number of moles that are found in the 9.2 grams of aluminum. Now I'm going to the cross stage, which is the Plato. I'm going to use the ratio from the equation in step 2 to work out how many moles of aluminum oxide are produced. Remember that I have only 0.34 or 0.34 mole of aluminum. So it is going to be easy if 4 mole of aluminum produces 2 mole of aluminum oxide, then 0.3 mole of aluminum is going to produce 0.34 multiplied by 2 over 4, and this is going to be 17. Just let me bring my laser. Again, the cross stage. So if 4 mole of aluminum produce 2 mole of aluminum oxide, then or so 0.34 mole of aluminum produce 0.34 multiplied by 2 over 4, which equals to 0.17 mole of aluminum oxide. That because and it is obvious, if 4 give 2, that means 2 give 1. If we divide this by 2, it's going to give me 0.17. Very simple, very simple. But I use this because you have to remember sometimes the calculations are not correct, because this is you just take 2 by 4, and then you have 2 down and 1 4. So this is going to be divided by 2. But sometimes in calculation doesn't comes like this. So you have to use the cross formulae, how you can bring the fourth unknown. In step 5, which is the cross stage again, work out the mass of this amount. Now I have the numbers of moles of aluminum oxide. Now I'm going to bring out how many grams in it, in order, because in the question he wants the mass. So it's going to be like this. We are going to calculate the relative molecular formula of the compound, which the relative molecular formula is equal to 2 multiplied by 27, which is the aluminum, and then 3 pi 16, which is for the oxygen, and this is going to be 1.07, sorry, 102. If we make the calculations, it's going to be 102. Then I'm going to use here the down stage in step 6, the down stage, to work out the mass of aluminum oxide by using the steps of the footbridge. Use the following formula, and this formula I bring it from our previous periods. The mass in grams equal the number of moles multiplied by the molar mass. So this is the molar mass. So it's going to be a number of moles is 0.17, and the molar mass is here, which is 102, and this is equal to 17.34 grams of aluminum oxide. Now I think it is very nice and you can understand what is going on. Go step by step and you are going to form and follow and finish everything. And we are going to exercise more 5 problems so you can understand all these steps, and we are going to see them in 2 scenes, step 1 and 2 and 3 in one scene, and then the other steps, the other 3 steps in the second scene. Let us go. Here is problem 1. Before we start problem 1, be sure that you understand each step of the previous examples, because if you do this, we are going to solve any problem in your mind regarding the same ways that we have. Now, our first problem say that what mass of oxygen, so the demand here is oxygen mass, combines with 32 grams of methane when that gas is burnt completely in air. That means we have an abundance amount of oxygen. And here he gave us 2 things: the relative atomic mass of each of the components, and also gives us the balanced formula or equation. Now, what we are going to do, this is the relative atomic mass, and here is the equation. So he put the gram, so you understand this is in gram, and this is actually an experiment. Now, step 1, again, write a balanced equation for such reaction. And here I wrote given. So you are not going to establish a new one. You are going to bring what the problem gave you and you put it here. I don't need to use these ones. It is not necessarily. We are going to use it sometime. Now, from this equation, I will say 1 mole of methane reacts with 2 mole of oxygen to produce 1 mole of carbon dioxide and 2 moles of water. So the ratio is 1 mole to 2 mole. This is about the reactants. I don't need the products here because he asks me about the reactants. Oxygen combines with methane. So he is talking about the reactants, not the products. So I don't need to use this information. I need to use this information. So 1 mole of methane, this is 1 mole, with 2 moles of oxygen, and that's it. This is what I want. This is the one that I want. Now I'm going to use the footbridge. So here is the upstage. I'm going to convert this 32 grams of methane into moles by using steps of the footbridge and using this formula. The number of moles equal the mass in grams over the molar mass in gram per mole. Now the relative molecular mass of methane is 12, which comes from carbon, and 4 hydrogen, and 1 is the atomic mass of hydrogen, and when I add these together it's going to give me 16. So if this is the number of moles, so each mole of contains 16 molar mass. So what I'm going to do is just I would like the number of moles of this one, so it's going to be 32 over 16 this one gram per mole. I'm going to have 2 moles. So in this 32 grams of methane, I have only 2 moles of methane. Now this is the first scene. In the first scene, the object of the first scene is to find out or work out the numbers of moles of one of the given items in order to solve my problem. Let us go for the second scene. Now here still we are going to use the footbridge protocol. That means this is the cross bridge or cross steps. This is what I'm going to do now about that. Now in stage 4, I'm going to work out. We will do this together. We are going to work out, or we will work out how many moles of methane completely reacted with oxygen. So 1 mole of this one reacts with 2 mole of this one. So 2 mole of methane reacts with 2, that means 4 mole of oxygens. Now in step 5, I'm going to have the relative atomic mass of oxygen here, which is 2 multiplied by 16, because those are 2, is 32. Now in step 3, why I use this in step 4? Because he asked about this. He demanded the mass of oxygen used. So I'm looking for the mass used here. Now I have now 4 moles. Remember, I bring out or work out it and it comes 4 moles. So instead of this, I'm going to say that mass in gram equal the number of moles multiplied by the molar mass in gram per mole. So this is the mass of oxygen needed to react is 4 multiplied by this number. This is the number of moles, which is here. I bring it from here. And this is the molar mass, which is 32. So it's going to be 4 multiplied by 32 is 128 grams. So for my solution, in order to have this 32 grams of methane to react completely and to bring me what? We need 128 grams of oxygen in order to fulfill this type of reaction. Follow this solution step by step. Do not jump or skip any step, and if you do not understand the step, you have to work it out several times in order to know why we use step 2, why we use step 3, why we use step 4, why we use step 5, and what we need in step 6. This is very, very important. Let us move and see what is going on in our delicious lecture. We come here for our second scene in problem 2. It is going to be a little bit, it's not difficult. It is the same like the previous one, but we are going to practice more with different numbers and different types of compounds. So it calculate the mass of iron 3 oxide produced when 74 grams of iron reacts with oxygen in excess. Again, the word in excess, that means oxygen is in abundance, and that means there is no problem with the oxygen. Oxygen is going to be there till the iron is completely reacted with it. So in excess, in abundance, fully, completely, all these tell us that this is not a limiting compound or a limiting product. So we are going to talk about this in the next lecture, but leave it now. Just remember that in excess means in abundance. That means there is no problem with oxygen. We are going to do the same thing. Write a balanced equation of such reaction. Here, nothing but iron third oxide. So you are not going to be use Fe or the isotope 2. You are going to use the isotope 3. And yes, the transition actually, the transitional element. And then you are going to use this information is 74 grams. That's it. This is the only information that we have, and we have to go through this. So we are going to build our house brick by brick. Now, first step is to write a balanced equation. And if we have this equation, it is now balanced. You can check that. Now, when I do this, I'm going to bring out the mole ratio, which is very important step in order to find out the numbers of moles. So here, each 4 mole of iron reacts with 3 mole of oxygen to produce 2 mole of oxygen, iron 3 oxide, this one. Then the ratio is between this one and this one, because there is nothing but this one and this one, and C here is as 4 mole to 2 moles. Based on this, I'm going to step 3, that the number of moles equal mass in grams over the molar mass in gram per mole. So what I have here is the iron. The relative atomic mass of iron is 56. I bring it from here. So and what does this means? It means a periodic table. Now, so the number of because he didn't give it to me, I should go to the periodic table in order to bring on the table the relative atomic mass of iron. Then the number of moles of iron equal this amount of iron over this amount, which is the molar mass in gram per mole, and it is 1.321 mole. Now I have 50% of the problem is solved. Let us go and see the other 50%. In our first part, we just complete the reaction. We did all our stuff and also bring out the number of moles of each. Now here we are going to do something else. We are going to see the second phase of the, or the second part, second portion of the problem. Now, steps 4, we are going to deal with the ferrous produced by 2 moles of how many ferrous is going to be produced, how many is going to be 6.667 of ferrous 3 oxide is going to be produced. Now I'm going to calculate the amount of this. I'm going to calculate the molecular relative molecular mass of iron 3 oxide, which is going to be 2 multiplied, because I have 2 here, so 2 multiplied by 56, I bring 56 from here, and 3 multiplied by 16, I bring 16 to here, from here, and all of them equal 160. Then I'm going to use the down stage, and using this formula, mass in grams equal the number of moles multiplied by the molar mass in it. And then what I'm looking for is the mass of iron 3 oxide produced by this reaction, which is I'm going to multiply this by this. So this is the number of moles, and here is the molecular mass, and this is going to be 106.72 grams. Very simple. If you do it as simple as it is, you are going to be pro in this. Trust me. Coming to problem 5, we are going to use an example that we already have used it before. So I'm not going to work with it too long. I'm going to quickly finish it because we use it. We just change some information in it, and also the demand is changed. So you have to be careful about that. Why I bring this, which we have already used, because sometimes you have to squeeze the information that you have in order to understand all aspects of the problems. Now here, our third one says that calculate the mass of carbon dioxide produced when 14 grams of methane is completely combusted. Combusted means burned out, everything finished on it. So, and also when we say completely combusted, that means the amount of oxygen used in order to oxidize this methane is completely in abundance. It is there in abundance. It is there in excess. So it's not a factor that will limit the reaction. Now, we are going through the same story. Step 1 to step 3 in order to determine the number of methane, the number of moles of methane. We are going to follow the same thing, and I will let you go through it one by one. The same thing that we have already done. Write the equation, come out with the proper ratio based on the equation. Don't bring something and then you bring another thing which is different. The ratio should be a symbolic for your equation here. If your equation is wrong, you are going to get this wrong, you are going to get this wrong. Now, step 3 is that you have to use this in previous information, which is the number of moles equal the mass in grams over the molar mass in grams per mole. And then you bring out the relative molecular mass of methane, which is composed of those two elements. So it is carbon, which is here, it is 12. The mass of carbon is 12 multiplied by 1 because there is only one, and then 4 multiplied by 1 because 1, which is the relative atomic mass, multiplied by 4, which are the number of atoms, and when you add them together is going to be 16. I have here 14 grams of methane, so the number of moles of methane multiplied is the mass in grams, the 14 in grams, multiply or over the molar mass, which is 16. So it is 16, and when we make the calculations, it's going to be 8.875 mole. So it's not complete mole, but it is around 88 mole, 0.088 mole. This is the first 3 steps. The object of the first 3 steps is to come out with the number of moles that one of my reactants or products are, we can get it. Now, I have another 3 steps to bring out the mass, because what you want is the mass, the amount of mass. So we would like to have the mass. How much mass, how many grams we have of this. Let us go and see that. Now, the object of the other 3 steps is to bring about the demand. What is the question of the problem? So I have the first 3 steps that bring about the number of moles of one of my compounds. The second 3 steps is going to bring me about the demand of the problem. Now, step 4, what I'm going to have the reactants, how much produced by methane by the reactant. So it's all, again, because 1 to 1, it's going to be 0.875 moles. Now I'm going to work out the mass of the amount of this one based on the relative atomic mass, relative molecular mass of this one, of the carbon dioxide, because this is a demand. The carbon dioxide is 44. So I'm going to multiply 44 by this one using this formula. Mass in grams equal the number of moles per multiplied by the molar mass, and it's going to be this one. Very simple. So the mass of carbon dioxide, which is the demand of the problem, is going to be 0.875 multiplied by 44 equal 38.5 grams. This is the way that I solve my problems. And if you go step by step, again, I promise you are going to be bro in osteochemistry. Now, in this fourth problem, we would like to use, actually, I would like you to pay attention to it, because understanding the problem and what is going on and the wording is halfway to solve it. Okay, so what our problem says, it says what is the mass of calcium that completely reacts with oxygen to produce 89 grams of calcium oxide. So what information that I have a calcium as a reactant, oxygen as a reactant. They react with each other to give me calcium oxide. However, I would like to know the amount of calcium present which react with oxygen to produce 89 grams of calcium oxide. So I'm interested of calcium and calcium oxide. Oxygen is not of my interest. Why? Because it is abundance. I don't need it. It is not a limiting factor for the reaction, so there is no problem. What I'm going to do, I'm going to solve the problem the same way that I have. However, in step 3, I have to consider something. Now, let us go for step 1, is just to write a balanced equation for such reaction. Since that the equation is not given by the problem giver, so you have here to form this problem, form this formula or the equation. It is 2 calcium atom plus 2 oxygen atoms gives me 2 calcium and calcium oxide molecule. That's very simple. Be sure that it is balanced, and that's it. Step 2 is to find out or to work out the mole ratio between the reactants and the product. Okay, so I have 2 moles of calcium reacts with 1 mole of oxygen, gives me or produce 2 moles of calcium oxide. And since I'm not interested with oxygen, I'm going to exclude the oxygen here. And the ratio is going to be 2 to 2 or 1 to 1. Both are the same thing because they are going to cancel each other. Okay, so now I find I found the suitable ratio, which is 2 to 2 or 1 to 1. It is the same equivalent. Now step 3 is the important step, because here I have to come out with a number of moles of one of my elements or the compounds, the reactants or the product. What I have here, I have the amount of the product. So I'm going to use the product in order to solve my problem. In order to solve the problem, I'm going to use this equation, which is the number of moles equal mass in grams over the molar mass in gram per mole. And because I'm going to use the calcium oxide, I'm going to have here the calcium oxide for each, which is 40 for the calcium plus 16 for the oxygen. Is going to give me, when I make this, is going to give me 56, which is the relative molecular mass of calcium oxide. If I want to use 2 by 2, 2 to 2, I'm going to multiply this by 2. So it's going to be 112. But it is the same because it is 1 here and 1 here, or 2 here and 2 here. I'm going to make a series that have the same thing every time it add 1. So if I have 3 moles from here, I must gain 3 moles from here. That's it. Now, sorry. Here now I'm going to have the number of moles equal calcium oxide multiply calcium oxide is equal the number of moles of calcium oxide equal to 89, which I bring it from here, over 56, which I bringing from here, and this will come out with 1.598 mole. It is around 1.6 mole. Okay, and I use the up to 3 digits to simplify things. Okay, now we are going to forward in order to solve the other scene of the problem, the other side of the problem, because this is not needed. They don't need the number of. We need to use this in order to bring out the calcium, because what is the demand of this is the mass of calcium. Let us move. Now, let us go for steps 4, 5, and 6. We finished the first steps and we come out with a number of moles of the product. Now we would like to go forward and see how we can solve the other portion of the test, because the demand is the calcium mass, is a mass of calcium in this reaction. So what I'm going to do is that I'm going to use the information to work out how many moles of calcium completely reacted with oxygen in order to produce calcium oxide. So as I know that 1 mole of calcium produced by 1 mole, 1 mole of calcium produce 1 mole of calcium oxide, or actually 2 moles of calcium produce 2 moles of calcium oxide, and those are the same because 2 to 2 equal to 1 to 1. It is the same. 2 to 2 equal 1 to 1. So if you use the relationship 2 to 2 is the same as using 1 to 1. Here I'm going for the purpose of this work is to use 2 to 2. So 1.589 89 mole of calcium oxide is produced by 1.582 multiplied by 2 over 2 equal, you cross 2 with 2, and this is equal to 1.589 mole of calcium. So now from this I come out with the how many moles of calcium I require. Moles of calcium, not the mass of the calcium. So the moles of calcium is required. Now I am going to have the relative atomic mass of calcium and then express it as gram, and this is going to be the molar mass of it. So gram in moles. And then in step 6, I'm going to use this one, which is the mass in gram equal the number of moles multiplied by the molar mass. And then I have only 40 here. So this one multiplied by 40 is going to be 63.571 gram of 571 gram of calcium. So in order to make 89 grams of calcium oxide, I need to burn 63.6 relatively, or approximately 0.6 grams of calcium. Now you understand what I mean, and I hope that you be aware of the difference in wording on the problem. They may confuses you or may direct you to work something that is totally wrong and totally not needed. Thank you. Let us go forward for the last one. Now, this is the last one. I'm sorry for this episode that it's little bit long, but this is important, and we have to practice a lot of problems in order to master it, solving this type of problems, and you can do this with any type of things. Now, our last problem says calculate the mass of magnesium chloride that could be produced by 98 grams of magnesium. Assume that chlorine is unlimited. Now, let us analyze this one and see how the information is useful. First, the reactants are magnesium and chlorine, and the chlorine is in abundance. It's unlimited, so it's not a limiting factor. The magnesium, the reactant, the amount of it is 98 grams, and the demand is what they ask about is the mass of magnesium chloride. So they are looking for the mass of the product, not the reactant. The chlorine is not of interest. I don't want it. It doesn't make sense. It doesn't solve the problem because it is not a limiting factor. It is in abundance. Now, we will make the same thing of what we have. That right balanced equation of such reaction. Magnesium plus chlorine equal magnesium chloride. And this is a balanced equation. Now, step 2 is the mole ratio. Determine the mole ratio. 1 mole of magnesium reacts with 1 mole of chlorine and produce 1 mole of magnesium chloride. So the ratio between the magnesium and magnesium chloride, the two element and compound of interest is 1 to 1. This is important. Now, step 3, I'm going to have one of my elements or the product. One of them I have to bring out and come out with the number of moles that it has. Okay? In this case, I'm going for the reactant, the magnesium. So the number of moles equal mass in grams over the molar mass in gram per mole. And the relative atomic mass of magnesium is 24. It is here. And so the number of moles of magnesium equal 98, which is here. It is given grams over 24, which is gram per mole. And this is, when you do the mass, it's going to be 4.083 mole. Approximately 4.02, approximately. But, sorry, 0.08. Now, we will leave this as it is, wrap it, and go for the final steps, 3 steps, in order to complete the second portion of the problem, because they don't need the magnesium chloride, the magnesium mold. They ask for the magnesium chloride, the mass of magnesium chloride. So they want the magnesium chloride expressed in grams. Let us go and see what is going on. Now, this is our last one. And I don't want to bother you, but still you have to pay attention for that. Again, it is about the magnesium chloride, and it is continuing the solution of the last portion of the fifth problem. Now, step 3, as usual, we are going to work out how many moles of magnesium completely reacted with chlorine. 1 mole of magnesium produced 1 mole of magnesium chloride. So, for 4.083 thousand of magnesium produced by, we are going to do the same mass of this 1 to 1, and it's going to be 4.0283 of magnesium chloride. Then I'm going to have the magnesium chloride relative molecular mass, which is 95. And then multiply mass in grams with number of moles multiplied by molar mass. And then, so the mass of magnesium chloride produced equal to 4.084 multiplied by 59, which is 378.885 grams, almost 388 grams. This is how I deal with my problems and how I can solve it. I assure you, if you go one by one, you are going to have a good attitude of solving your problem. I wish you best luck. Now we come to the end of our period. I am sorry, it is a little bit long, which is maybe 70 minutes. It's around 70 minutes. It is a little bit longer than usual. But why we do this? We do this because it is important for you to exercise solving problems. So be careful about that. You are going to be master of this. Just take care and take care of the problem itself. Read it thoroughly 2, 3, 4 times. Pick out the information that is there. Every information, pick it and write it down, and then determine what they demand, what they ask about, and what information is given to you so you can easily solve this problem. I wish you good luck. If you have any problem, just write down in the comment section about that. Thank you, and I wish you good luck. Bye-bye. Have a good one.